So we're going to cover three major things that I want to look at today. One of the things that gets requested a lot is AI stuff. That's not going to be done today. AI, I don't even know how to start tackling that. It is such a gargantuan, massive topic. I have a book somewhere, a good book I was going to recommend to you guys, but I don't know where it is. Poop. It's such a broad topic. What does AI mean? Well, pathfinding is AI, and we've done that before. But you know, it's such a big topic, so what we'll actually have to do is break it down to specific little like sub things about what people mean by that. Hey Dan, thanks for the sub. So today what we're gonna do is look at other things that people ask for. One, more Blender stuff. Blender is not programming, but it's 3D modeling, it's free, and a lot of people want some extra info about that. So we'll look at that, we'll look at a couple of basic modeling things, and also another really cool trick to easily make things like more flexible terrain and things. We'll look into a couple of options that way. Hey, Falafel Waffle, thank you very much for the resub. And CSN Azalton, I never know how to parse your name. CS and Azalton? I don't know. And Servogelius, thank you very much for the new sub. So we're going to do that. Then what we're going to do is we're going to look at some Unity physics stuff. Because a lot of people have asked about sort of, like, basic Unity physics are fine for, you know, relatively slow-moving objects with a relatively simple movement. But some people want to know about just, you know, higher precision, faster moving objects, and we're going to look at that. And that's something I specifically have experience doing because I have worked on making a pinball game in Unity before. And that has some very funky quirks about what kind of expectation you have on the physics engine side of it, because it's very demanding to have very high precision physics. So we'll look at a little bit of that, and then we'll look at something pretty and look at real-time reflections in Unity using reflection probes over here. So, but we're going to save that one for last. Let me clear that out. And then what we're going to do is we're going to play some game. Try the CS as ketchup. Chanzolton. I'm just going to fail every time. I'm really sorry. CS and a Zoltan. All right. Maybe. Lots of people talking about programming in the chat. Different programming languages. Every programming language is poop, and every programming language is awesome. Holy wars about programming languages are silly. Except PHP is obviously the hellspawn of the devil's ass, and it's just terrible. There we go. RJ Helms, thank you very much for the resub. We're doing 3D physics today because we've done a couple of 2D physics more recently. So we're going to be doing 3D physics. Basically, our example in this will be a pinball, ball, and flippers. And trying to get that to work is not super, like, it's not obvious. And it requires that you mess around with some very basic settings of the engine to get the sort of performance and precision that you want. So we're actually going to start off in Blender, though. So Blender is a 3D modeling program. It is free. It is open source. It's very good. You can use this to render very high quality graphics and scenes. People make movies in Blender. People do all that kind of stuff. But specifically, we're going to care about it from the point of view of modeling for a game. Boom. So we're going to do a little bit of basic intro. What I need to do is turn on the... I forgot to do that. I want to turn on the... what's it called? It's like the keyboard and mouse viewer. Oh, I don't know. I don't know what it's called. Damn it. There's an option I can put which shows you what keys I'm hitting, but I'll just tell you what they are. All right, so you can use the middle mouse button to move around. It's not going to be a full tutorial, but it's going to be this. So what I'm going to do first is I'm going to set up the table that we're going to use to play pinball. Okay? And capture isn't getting full screen. Oh, thank you very much. Let me go and do that, followed by... No, more than that. Oof, more than that. So bring that over here, and then bring it down here. There we go. All right. I think that's better. Key casting, is that what it's called? Bum, bum, bum. I guess there was something when I typed in key. No, it's not that. And I think it's one of these plugins. Anyway, sorry, it's been too long. Let's just get started. I believe it's called screencast keys. A few people are saying that, but it's not an add-on. Maybe it's somewhere else in the user preferences. We're not going to waste time doing this. We're just going to move on. Because if we worry about these little things, we're never going to get anywhere. I was pretty sure it's a key, it's an add-on that's going to be turned on. Anyway, we'll figure it out later. Someone might look it up. Okay, so what we're going to do is we're going to start off by making the pinball case in this case. And this is going to look at very simple editing of cubes. And 90% of the time, or probably a hell of a lot more than that, probably more like 99% of the time, what you want to do is, and panel. What you want to do is start with a box. Display. People are telling me things. Editing virtual key. Everyone's telling me something completely fucking different, which is pretty standard Twitch. Everyone's saying something completely different that don't really add up. It's not under the end menu. So we're just going to move on. Fuck it. We're just going to move on. Shift-Alt-C. No, that's something else. Yeah. So, done. We're ignoring it. So, what we're going to do is we're going to start with that. And I was going to say, let's start this over. 99% of the time when you are doing modeling for a game and you're doing something in a 3D meshing program, you're probably going to start with a cube. And what's very common to do is to start with a cube, subdivide it down, and start sort of working it almost like clay, right? You can imagine that you've got a ball of clay, or in this case, a cube of clay, and then you're sort of starting to mold it and form it and work like that. And it's actually very convenient. Whether you're modeling like a human head or a body or a car or even like your world for a level mesh, you almost always start with a cube, and then you subdivide it, and then you start to pull vertices all over the place. And that's exactly what we're going to do here. Now, our actual pinball case is going to be a very, very simple objects. So one of the things, first of all, is your number pad, the 7, 1, and 3 key. These are the easiest ways to navigate around your view. If you hit 7, you're going to be looking straight down. If you hit 1, this is the forward view, and if you hit 3, you're going to be looking at it from the right or the left, one way or another. I'm not sure. You can also hold Control and do the opposite. So Control and 7 brings you to the bottom. And now, so we're under the scene looking upwards, for example. So I'm just going to hit 7 to look straight down. You can even see in the corner over here, the top perspective. By the way, if you started with a camera and a light in here, you can just select those and delete them either from the scene view in here, or you can just right click on them to select them, then delete them with a key. But we'll move on from here. So if you want to add a cube, the easiest way to do it is to do a Shift A over here and add a mesh. Shift A lets you add all kinds of different things. We're going to go and add a cube over here. What we're going to have to care about is the dimensions of our pinball game over here. You can get the actual dimensions online for most of this stuff. It varies a little bit by pinball table. If you just look up pinball table dimensions, you will get a lot of pages discussing different sorts of formats over here. I'm going to go for something real-ish. But the actual specifics don't matter too much. But basically, the width of the cabinet, well, I mean, the length of the cabinet is going to be longer than, or is going to be, the length is going to be more than the width, obviously. So the length of it will depend. We're going to work in centimeters here because naturally in Unity, 1 unit space in Unity is typically regarded to be 1 meter. And it's actually really good to use that sort of format as your basis, especially if you're going to be doing something physics oriented. And the reason is that most of the constants and everything set up in the physics engine are set up in such a way that if your objects treat 1 world unit as 1 meter, then everything will sort of look correct. Objects will fall at the appropriate rate. They will sort of skid around and slide around in a way that feels about right for their dimensions. But the fact of the matter is, it is tweakable, right? You can treat 1 unit in Unity as something different. You can treat it as an inch or a foot or a centimeter or different things like that. But then you'll have to go and adjust all the gravity settings and change a lot of your sort of friction settings, and also change how you treat the weight unit. When you set up a rigid body, there's a field in there for weight, which is sort of kind of more of a density setting. So it just works out better if you pretend that 1 unit in Unity is, or Blender and all these things, 1 unit equals 1 meter. Everything works out a lot better. So for our pinball machine, we're going to say it's going to be about 130 centimeters long. So our cube right now is a 2x2 cube, and we can clearly see that. Actually, if I hit, there we go, hit 5. The 5 key switches between perspective view and orthogonal view, and orthogonal view is a lot more useful for this. So we can see that the square, the cube here, is aligned. Assuming this shows up on the stream, I hope that these guidelines show up on the stream. I think they will. It's a 2x2. So we want it to be 130 units long. So what we're going to do first is we're going to hit the S key. The S key lets you scale things. Now, we're not going to just scale it by moving the mouse around. Instead, we can type things in. So I can say something. If I type 2, for example, I'm doubling the size of a cube. It's now 4x4. Okay, we've got that. I can hit Control-Z to undo it. What I'm going to do first is I'm going to halve the size of the cube. So I'm going to hit S to scale, and then I'm either going to type 0.5. That will have the size of the cube. Or you can actually go and type /2, divided by 2. So now we have a cube that is 1 unit in world space. So now what we want to do is we want to make it about 130 centimeters long. So what I'm going to do is I'm just going to multiply this first by 130 along, and this is a tricky part. Blender units are different. In Unity, the x-axis is left and right. That's the same thing in Blender. But in Unity, the y-axis is up. Okay? The y-axis is up in Unity, and the z-axis tends to be forward and backwards. Is, based on your typical alignment. But the important thing is that in Unity, y is up. But in Blender, z is up. So they use a different coordinate system. There's also a right-handed versus left-handed thing. But in any case, we know here we are looking straight down, and in the bottom left corner, you can see the little your little axis grid here, which shows you that on the screen, screen-wise, the top of the screen is positive y, the bottom of the screen is negative y, but this corresponds to a forward-backwards axis. So what we want to do is we want to stretch this object along the y-axis and make it 130 centimeters. So right now we've got a 1x1 cube. What I'm going to do is I'm going to multiply by the y-axis by 130, and then we'll divide everything by 100 after, right? So that we end up with actual meter units. So I'm going to hit S to scale, and by default, when you're scaling here, it scales the whole cube in every direction. But if you hit an axis key like Y, now I'm only scaling along the Y-axis. And I can still type in a number, say 130, like this. So technically right now it's 130 meters long, but we'll fix that in a second. So that's the length, and then the width, we're going to go for a width of about 55 centimeters, and it'll end up being okay-ish. Some pinball machines are different things, but this is going to be good enough for this. So again, I'm going to hit S to scale, X to only scale in the X direction, and I'm going to type 55. So now technically I'm 130 meters by 55 meters, so I'm going to take the whole thing, I'm just going to hit S, scale it by /100, I'm dividing by 100. And now we have something that is 1.3 meters long, or 130 centimeters long, by half a centimeter wide, or half a meter wide. Yes. So this is about, this is about right for a pinball table. It's not currently deep enough though. So what I'm going to do is change that. I'm just going to scale it in the Z, and I'm just going to pick some amount of height. Oh, it's not really showing it to me very well, is it? There we go. Scale it in the Z. Some amount of depth. I don't know. Something like this. This doesn't really matter so much, but this is the idea is the pinball case. Now, obviously, the play surface in the pinball table, things should be sort of, shouldn't you be scaling edit mode? That's an excellent question and probably true, but we're gonna be locking in these scales. This is actually, I'm sort of showing a bad way of doing it right now because what we want to do is apply the scaling afterwards. So yes, normally you should be doing your edits in edit mode, but we'll look at that. So we haven't looked at edit mode yet. So we've got this. Now what we want to do is we want the play area to be, to sort of have walls around it. Or more appropriately, I like to think of it as taking a sort of play area inside of this and sinking it down, right? So sinking it downwards. And that will give us a place where the ball will be contained and can't get out. So that sounds like a pretty good idea. So for this now we have to enter edit mode. And so right now we are in object mode. We are working with this object. We can move the whole object around and we can scale the whole object around, which will have certain implications with Unity, as we'll discover later on. Probably. I don't actually know. If this is the only object in the scene, then yeah, it should result in something being wonky in Unity. And here's why. Basically, the way this object is defined now, when you go in edit mode, that's when you can grab individual vertices over here and just stretch them out and do weird things like that. The coordinates of these vertices in edit mode are a certain number base. And then if we scale things in object mode, that doesn't change the coordinates of the vertices, which means when you pull this into Unity, weird things will happen, because what Unity will remember is that, or what Unity won't really be aware of properly, will be these scaling changes over here. You see how the scale has all been set? And these are the numbers. This is all the math that we've done. We started with our 2x2 cube, and we scaled it in a variety of steps, but ended up with this as our overall scale over here. What we'd like to do is apply these changes so that they get baked into our model properly. And this is something, if you don't do this, same thing happens if you end up moving it or rotating it here in edit mode, you will be changing these numbers. And you usually don't want these numbers to be anything except, you know, like 0, 0, 0 across the board. Well, I guess scale would be 1, 1, 1 across the board. Otherwise, weird things can happen when you pull into Unity. So what you're going to do, there's a nice trick in Blender. If you don't know where a command is, hit space, you get this little search box. And what you're looking for is something called apply object transforms. Transforms, you should know from working in Unity, are when you transform something, your object transforms your position, your rotation, your scale. Well, we want to apply all the transformation changes we've done here and bake them into our model. So we're going to say apply object transform. We're going to hit enter. And, I was expecting a pop-up. We want to apply the scale. There we go. And now you can say, if we do that, you see how now the scale is 1, 1, 1 across the board. And so our changes have been baked into this object, which is great. All right, so now we're going to go into edit mode here. You can alternate between edit mode and object mode by hitting tab. So in edit mode, we can actually see the little vertices over here, for example, as opposed to object mode where the whole object is selected. So we go tab, we are now in edit mode, and you can tell that by the little pull down menu down here. Yes, there's shortcut keys as well. The edit mode down here. So what we're doing is we're alternating between object and edit. And in edit mode, there are 3 ways you will generally modify your model. Either you with face selection, edge selection, or the most common, almost certainly, is your vertex selection mode over here. So in vertex selection mode, you can grab one of the vertices, one of these points. You select things by right-clicking in Blender, by the way. So you right-click, and that selects a vertices. If you left-click, you're moving this 3D cursor around, which has usefulness, but isn't what you're looking for most of the time. So instead, you're going to be right-clicking on things, and then you can still apply the other keys. So you can actually drag things by pulling on these little arrows. Sometimes you do, it's handy to move along a particular axis, but normally, if I want to move this particular vertex, I would hit the G key, which I always think of as grab, and then you can move things. Then you can still lock it to say, hit X. Now I'm just moving along the X axis, for example. But what we want to do here is we want to go and sync a part inside here. So how do we do this? Well, the common way to make changes, once you've got sort of your block relatively the right size, usually the next thing you start to do is extrude things. And so this is how this works. First things first, some things, there's one little thing that will get you every time in the default settings in Blender. Let's say I want to select all 4 vertices on the top of the screen, right? So on top of the box, I want to select all 4 of these vertices. So let's say I go into one of the side views. So I got 2 side views here. And I use the B key. Let me just unselect. By the way, this is really handy. If you hit A, it selects all. Or if you have anything selected, hitting A again will deselect all. You will see me do this constantly to make sure that I don't have anything selected accidentally. So let's say I go into the side view. Then you could use the B key for a box select. And then you can click and drag to select things within the box, which is really handy. So I've selected these 2 vertices. But then if I move my view around with the middle mouse button, notice only the 2 vertices in the front were selected. The ones in the back were not. The reason for that is, by default, Blender has this button selected. Limit selection to visible. It will only let you select things that you can see. Sometimes that's really good. For example, it stops you when I'm over here. I'm going to hit A to deselect everything. If I want to select this vertice, I can just right-click on it and select it, which is great. It would be kind of annoying if I went to select this thing, and I was accidentally selecting the vertice in the back. So by default, that's turned on, so you can only select things sort of in the foreground. But sometimes it's bad. If you toggle this off, now you can select things in the background, plus it gives you sort of this X-ray view where you can see through it. So now I can click on the thing and select the thing in the back, even though I don't have it. This option is moot if you are in a different viewpoint shading. Right now we are in the solid viewpoint shading, so objects, let me turn this on. So objects are rendered in a solid fashion. If you change this to say wireframe mode, where you can see through the object because it's just a wireframe. In wireframe mode, you can always select objects in the background. In fact, that little button goes away completely. So you do have the option if you just if you stay in solid mode and you leave this on. So in solid mode, you can't select things in the background. And then if you switch to wireframe mode, by the way, hitting the Z key lets you toggle back and forth between these, very easy. So then you could toggle to wireframe mode, select things in the back, do your work, toggle back to solid mode. Now I can only select things in the foreground. Really good. So what I'm going to do here, I'm going to go to wireframe mode, and I'm just going to go and box select the top. There we go, and I've got that. And yes, someone said in the chat, you can also use the C key to sort of paint selections of things. Although, again, even with the C key, if you are in solid mode, it will not select things in the background. I'm like painting around here, painting around here, painting around here, and I look around, it did not correct the point in the back. So usually, I personally don't end up using the C key very much because I like the precision of the box key. But I think that's just because my hands are shaky as hell, and so I suck at using the C key for selecting things. So front view, select all the top faces like this, or the top vertices. So effectively, we've got the whole top face selected. Then we can hit the E key to extrude, right? And then we've built a whole new set of faces on the side and expanding this outwards. And then you can take this top bit, move it around, scale it, you can do all kinds of different things. And so this is naturally how you build up a lot of geometry in your modeling, is you've got your basic form, then you extrude bits out. You know, think about like if you're making a body, you might have a torso and then extrude out an arm and another arm and so on and so forth. If you need more precision, so I'm just gonna back up here. I'm hitting undo to get back to, you know, my normal box. If you do, I think there's a key over here. I think there's buttons. I mean, there's buttons for everything. I guess it's loop, cut, and slide, isn't it? Yeah, Control R. I never use this. So loop, cut, and slide, or Control R, is quite nice because it lets you put a new cut somewhere. So say here, and then once you've got that, if you want to pull out an arm, well, it might be a pain for you to select the vertices. You might actually prefer being in face selection mode here. Select this whole face and extrude that out there. So I'm just going to undo this. There you go. Very powerful tool. So what we're going to do for a pinball, though, is slightly different. I am going to go and select all the top faces. I'm going to extrude outwards, but then I'm going to hit escape. So what this has done, now this can catch you off guard, this has not canceled the extrusion. It has simply canceled me moving the extrusion. If I hit the G key to get grab mode again, you can see I still have this extra little bit. But right now it's in exactly the same place as the other one. And this is a really common trick that I quite like to do, is I'm going to scale this down a scooch. I think what I'm going to do is I'm going to scale it down in all directions right now, and then I'm going to scale again in the Y to bring it up. So that way, the sort of space on all four sides is about the same. So now having done that, what you can do is extrude from this part, either up, or I'm actually going to extrude downwards. So now, I have my little pinball area, right? Boom. Looks sane. Yeah, there's lots of different things you can do with inset, but I like using one tool and then it's easier to teach. So we got that. Technically, most pinball machines will have the back plane up a little higher like this. And obviously the whole thing should be tilted, right? We're not going to tilt it here. In fact, we're not going to tilt the pinball machine at all. Instead, what we're going to do is tilt gravity. It's going to make life a lot easier for us. But there you go. So we have our pinball case. Now, what we haven't done is done it in UV mapping over here. I'm going to hold off on that for now. We'll probably go and insert UV mapping when we try to mess around with reflections to make them look cool. But that's my table. There are many like it, but this is mine. I guess for a slightly more natural table, we need the little skirt at the bottom here. Now, so far what we've been doing is modifying one object, but we can have more than one object in here. For example, I could put in another cube. Now, it's worth noting the cube will appear wherever my 3D cursor is. So it'll be centered over here where my cursor was. If I undo and I click over here, and then again I add another cube, Nocturnal Android, thank you very much for the sub. I know I've been missing a few here. MJ Koo as well, thank you very much for the resub. So you can see the cube shows up wherever your cursor is. But you can move it, you can do all sorts of things. I think, is it, what's the hotkey to reset the location? Oh, it's been too long. Or clear. It's clear transforms, isn't it? Clear rotation, clear origin, clear parent. Is it Alt-G? Yeah, there you go. So Alt-G will clear the... So normally G moves, R rotates, and S scales. So the Alt version of it clears it all the way. So this is going to be the skirt. So what I'm going to do is I'm going to go into edit mode right away. I'm going to shrinkify this down like this. Bring this down like this. Zoom in. Could be doing this a little bit more precision, but that's okay. And bring up the X. I'll actually get it to intersect the walls a little bit. That's fine. We're going to bring it into this side view. I'm going to shrink it along the Z axis. Actually, let's bring it into this side view. Bring it up this way. Again, I'll get it to like poke into the ground a little bit. Actually, a little bit more is fine. What we're doing here is this bit of the pinball machine, where you've got sort of something like this. We're going to use the loop cut tool, and if you mouse wheel up, you can make multiple loop cuts. I'm going to make 2, and I'm not going to slide. I'm just going to hit escape to lock in that location, and then I'm going to bring this down like this, and then I'm going to make another pair of loop cuts there, and then what? Ah. Then we got to make a little bit of a hole here. So I'm going to make a... Whoops, that's not the way I want it. I want you cut this way, bring it down there. And then what I'm going to do is I'm just going to remove this face. So if you hit escape, you can delete. I'm going to delete only the face. So now if I go into here, I effed up. I removed the wrong one. There we go. Now I got a little hole for us to lose the ball in. Hooray! There we are. So that's going to be our pinball table. I'm going to name these objects. I'm going to name the first cube here. I'm going to name this as, I don't know, table. Looks good. Lolor, thanks for the resub. Then this bit down here, I'm going to name this the skirt or apron. It might be called the apron. I don't remember. One or the other. You know what? I actually don't like the way... I don't like the height here. Let me change this. This should really be more like that, I think. There we go. That looks a little bit better. All right, good enough. So I'm going to save this. I had already picked a location for it. And if we take a look at Unity over here, I've got my meshes and this table, and I can drag this into the game world. And there it is. We're going to go ISO view, lock in on that. And there's the table. Let's give it just a little bit of a texture in here, just a custom material to make it look a little bit more obvious what's going on. Just a little easier to see. I'm just going to get a skirt material that is just slightly colorified. Just a little bit of a pale blue. So this is our table object here that we have pulled in. And you can see it's got two sub-components, the skirt and the table. So on the skirt, the mesh renderer there, I'm just going to give it... Oh, and then the material, I'm just going to replace the material. There we go. So now we can see it a little bit better over here. In the game view, we don't have much, just a little black square. Because of why? Well, first of all, the camera is not set up in a useful place. I think when I created this project, I was using the 2D settings. Yeah, because it's, we got to set it to perspective camera. And obviously, we have to bring it up. I have to center it along the X. There we go. We have to, I'd say, a little closer. And a little downer, and then we got to put in a light because everything is dark. So we're gonna go game object. Who's that? Ed Surfer Guy. Thank you very much for the resub. And a light and a directional light. There we go. Oh, the wrong way around. I think for the sake of easier 3D modeling, I'm just gonna bring the camera over here and then rotate it 180 degrees along the y-axis. There we go. Bring you in like this. Maybe a little higher up, a little lower down. There we go. Yay! All right, simple modeling. Now let's do something Very cool. What is a pinball game without a ramp? And this technique is going to be a sort of thing that is going to be awesome no matter what kind of game you're making. This is a super, super cool trick. Do I want to keep modeling in the same place, the same thing? Yeah, sure. Let me just move off to the side for a little while first. So here's what we're going to do. Imagine any kind of game where you want something, hey Slovenian Devil, where you want something sort of repeated, right? Whether it's a road, or in this case it's going to be a ramp, or I don't know, chains, or anything that you might want to, I like the idea of having one core component that's repeated over time. This is very easy to model over here. So we're going to add a new cube over here. All right, that's huge. I'm going to go into edit mode. I'm going to scale it way down. Then what I'm going to do is I'm going to go to, I don't know, the side view over here. And how do I want to do this best? I guess what I'll do is I'll do a loop cut like this. And then with that part selected, I'm going to scale along only the Y. And bring it over like this. There we go. And I'm going to get another pair of loop cuts here. And again, I'm going to scale along the Y and bring it almost there. And then I'm going to grab just the top bits of this inner one and bring it way down like this. So we've got this sort of like trenchy kind of thing. I don't think it needs to be quite this tall. I think something more like this will look good. So the idea is this is going to be used to make a sort of a ramp. I could have made the geometry for this simpler. I wonder if I should have. Because I don't know if we need these angled sides. You know what? Let me back up here. I'm going to do that. I'm going to make it simpler. And I think the easiest way to do that, actually, is to go back to just the cube. And instead, bring this down like this. Oh, I can show off the mirror modifier. Let's split this exactly in half. Then what I'm going to do is box select everything on one side, hit X to delete the vertices. Now we only have half the object. But we can add a modifier here for mirror. Oh yeah, I'm working on the wrong angle. I wonder if that's going to come and bite me in the ass. That's okay. So the mirror modifier allows you to mirror along an axis. And we're going to mirror it along the y-axis. And now if we look, so we've got the full object. But now any changes I make to one side will be made on the other. So now if I go and say extrude over here, see how it's happening on the other side? And then grab here and extrude upwards. There we go. And if I pop out, voila. It's a little easier to manage. Okay, I think that's just simpler geometry, and that's great. All right, so we've got that. We've got this object here. And what I want to do is I want to repeat it. So what we're going to do is we're going to throw another modifier on here. This one's going to be the array modifier. And what's cool about this one is it just repeats this way. Now, you can change the direction that it repeats. It's this relative offset thing. Right now, it's offsetting in the x direction. I could set this to, say, 0 and instead offset in the, say, y direction. That'll offset this way. So you can change that around as needed. But I'm going to leave it like this, and that's going to be fine. And this is relative offset is probably what you want. It'll offset by the exact length of this particular component as opposed to an actual fixed distance. So now you've got this repeating thing. That's kind of handy. But I mean, all right, I could have also just made it longer. So is there something cooler we can do with this? And the answer is absolutely yes. And I actually did this. If you check out my programming channel, I did a video on curbs and NURBs and things like that. You can look that up. And I show you a neat trick that we can do something very similar to that. Muli Puhuja, thank you very much for the resub. What we're going to do is we're going to add a new object here. We're going to grab curve. And I'm going to take, say, I think I want the Bezier curve for this. I think that's going to be quite good for us. So this is a curve. This is the default one. You can go into edit mode on this. And what's cool about the edit mode is not only can you move sort of the points. So if you hit the G key over here, I can move the point. But what you can do is grab these handles. Again, you can right click to select or box select or whatever. And hit G, and you can move the handles around and affect how the curve happens. You can also subdivide this. You can't, as far as I know, you can't use Control R to do the loop cut. But what you can do is if I click here and I hold Shift and I right click here, so I've selected both those points, there's a subdivide button right here. You can also just hit W, which is usually what I do. Subdivides it into two. And now I've got another point that I can mess around with. Very cool. So there's lots of things you can do with this. You can actually do a certain amount of modeling with the curves by having them be physically present. There's a little curve tab over here, and you can give them a certain amount of geometry and things like that. But that's not what we're using this for. What we're going to do here is we're going to right-click back on our object over here, the thing that's got the array modifier. So look at the array, the modifiers here, which is the wrench. So the array modifier has a fit type over here. Right now we're working with fixed count. We're saying we want 16 iterations of this, or whatever. You can pick a different number, that's fine. But if you click on this, you can also say bit curve. If we pick that, then it wants to know what curve to use. So if we click here, it'll give us a list of all the curves. We just have one. It's called Bezier curve right now, so that's good. We're going to click on that. And now what it is doing is it is using the length of this curve to tell you how many iterations to have. So as we change this curve, we change that. Now that's pretty cool, but that's only part of what we can do, because what we'd also like to do is have this follow along. And I'm trying to remember. I think for this we use, is it the curve tool? One moment. Yes, yes it is. So let me rewind here. So the array modifier, we told the array to use this curve to figure out its length. Then you add another modifier over here, the deform curve, and then you tell it what curve to use to deform this object along. And what we do is we take the same object. Now, things look a little funky here. The reason they currently look a little bit funky is because these two objects are not at the same place, physically speaking. You kind of want them to be in the same area, and now that we've done that, it becomes very obvious what is happening. And if I modify this curve, you can see that everything else about my object starts to change. That's very cool. Right? All I'm doing is selecting things, then I'm using the G key to drag things around. And again, you could subdivide this further and get even more control. If I switch to a side view over here, I can raise things up as well. And like that. And again, as I change the length, the array creates more copies of the object. The sort of thinner your object is, the more instances of the object it will take to fill this in, which does mean you'll get something a little bit smoother, although it also means a lot more vertices. This length tends to lead to something that is visually works quite well, especially if you make sure that your objects get merged. So in your array thing, hit the merge thing, and never mind, that's not what we want. Oh, the distance is off. Really? They're actually so close that they're merging in a way I don't really want. There we go. So this should mean that any vertices that are literally touching will merge together. And then if we add, if we take this and we say you should be smooth shaded, it'll look a little bit funny, but then we're going to add yet another modifier here called edge split. And what this will do, especially as we change the split angle, no, I'm going to combine them properly. All right, we'll ignore this. Let's not worry about this, because it'll take too long for me to fiddle and get it to work properly. But you could get it to look a lot smoother here. We'll just go back to flat shading this, and that's going to be okay. All right. So we've got that. You can also, if you look at your array, you've got this option of putting a start cap and an end cap. This means, here's what this means. We could, if I take this original, my array object, I'm going to hit Shift D to double it. I'm going to move it over here, and I know it looks really wonky now because I'm moving it away from the curve, but on this copied one, I'm just going to go and remove the modifiers. Well, I'm going to keep my mirror modifier in here, but I've got just the initial little stubby bit. And what I'm going to do is I'm going to take this initial little stubby bit, I'm going to go back into edit mode over here, and what I think I'm going to do is I'm going to go into wireframe mode, I'm going to grab the left edge, I'm going to hit E to extrude. Then I'm going to take this top bit and sort of move it out this way. And I guess I'm going to pull it out a little bit more and maybe a little bit more like that, right? The idea is to try to get sort of an opening area. And maybe I guess what I can do is grab these bits and sort of bring them out that way. There we go. So now we have what looks like it should be the entrance to our ramp, right? And what I can do, let me name this to something called ramp entrance. And then let me go back over here to our array version of it and take a look at the modifiers. And if you look at the array modifier, there's that start cap. If we go and grab the ramp entrance from there and put that there, check it out. It just grabs this object and glues it onto the front. It works a lot better if you copy your initial object and put it there. It works great like that. We could also take this and, there's lots of reasons it wouldn't make sense. If I put the ramp entrance as the exit, yeah, I was going to say it's probably pointing the wrong way. And it doesn't matter because we wouldn't want that particular ramp entrance over there. We'd want to build something completely different for the exit. Maybe something kind of round with a hole in it so that when your ball gets to the top of the ramp, it then has something to fall through, for example. But I think that looks very cool. So let's get this thing inside of our little area over here. So what we're going to do is I'm going to grab the Bezier. So this cube here, I'm going to rename to the actual ramp. There we go. So I'm going to grab the curb and the ramp just by holding shift and clicking on them both. Now what I'm going to do is rotate the whole thing. I'm going to scale this all down. But you see, weird things will happen by doing this. But what I'm trying to do is get the ramp components to look kind of vaguely right. And then once that looks right, I will go and apply. It's Control A. I want to apply the, say, rotation and scale. Lock that all in there. Ooh. Hang on. Yeah, I'll actually also want to grab that. Scale everything down for it to make sense. Control A, apply that. And are we still looking okay? No, not really. How come? Yeah, normally I would have built it here and to scale appropriately. It's because I went off to the side. You know what? Well, there's a couple of different ways I can fix this. I'm just trying to think of what the best and easiest way to do it. And what I'm wondering about is just scaling it down in Unity and placing it wherever the hell I want in Unity. I could make the pinball machine bigger, but I'm trying to end up with like an appropriate scale in the first place. I think what I'm going to do is I'm going to undo some of the linkage here and make sure that everything looks good independently. So I'm going to get rid of the curve and array. See, you're fine. You're fine. You're rotated oddly, though. Clear the rotation. There we go. That's probably part of it. And apply the scale and rotation, and apply the scale and rotation. And you over here are going to apply the scale and rotation. Let me try this again. Now that everything's been sort of fixed independently. Array, fit curve, pick the curve. That looks right. I think now we're going to be fine. Add modifier curve. You're going to be linked to the curve itself. And that's when you go weird. This part is fine. I think scaling the curve might be a mistake. Let me take this, delete that, create a new curve. Instead of scaling it at all, I'm just going to bring everything a little closer together over here. Let me try this again. It's been a while since I've done this. You're fine. Oh, you also, it may be because they weren't in the same location anymore. Because that's going to look intentionally screwed up, and that is very true. There we go. Now we're good. Okay. And then I'm going to tell the array that it should have a start cap again, which is that. Excellent. And then if I move the curve and the ramp together, we can move you over here. Everything is fine. There we are. And oh, that was the other thing. I was rotating the base ramp bit. You don't want to do that at all. All you want to do is edit the curve. And rotating my ramp is basically just moving my curve around. That's what I was screwing up. It's because I was rotating everything together, which you don't want to do. Okay. Like that. And I suspect this might not be big enough for a ball. How do we know? How do we know what our ball size should be? Well, we can go and add a circle. Not a circle, sorry. We can add a sphere. Now, it's obviously quite huge over here, but we can change this sphere. Right now, it's got a radius of 1 meter. The correct diameter of a pinball is 2.7 centimeters, which means that the radius is 1.35 centimeters. So if we want that to be correct, we want 0.0135 meters will give you a ball of the appropriate size, which means we can then move it here, and we can see, well, that's not going to fit. So that's okay, because we should be able to go and take this, and editing it now should work in real time. It does. Obviously, the base ramp doesn't, but we can fix that later on. So if we pull this out a little bit more, tab out, there we go. Now it looks like the ball should be able to fit this. Cool. Let's just remove the end cap, or the start cap for now, because this should be the correct size ball. It looks like it will fit this. Obviously, our walls need to be brought up now because they look too short to contain this. Let's bring it up kind of like that, maybe a little bit more. There we go. That all looks vaguely correct. And vaguely correct is what we're going to go for right now. So, and then we're going to go and just try to get this positioned. Well, we are way too low. So, all I have to do is grab the curve part and just edit this. Everything we're going to do is in here. So I'm going to bring this up, bring this other side up higher. There we go. And that's going to be our ramp. And bringing this here, I'm just going to make sure that the ramp clips into that surface a little bit, just to make sure there's not a little weird edge that is going to be a pain for us to deal with. There we go. Just something like that. That way, we should be able to send the ball up there in some fashion. All right, so now that we've got that, we can save this. And if we go over to Unity, it'll reload the model for us, which will include our ramp. And there you go. So you can easily imagine, I think, using this sort of mechanic with the array plus the curve to build roads, to build all kinds of really good things. Another thing, and this is not going to be included in this particular tutorial, but even if you're making a 2D game, consider this. You're making a 2D game. Let me go and clear everything. I'm going to hit A to select all the objects. I'm just going to delete everything. Let's go and hit Shift-A, add a mesh, and just put in, I don't know, just a plane. A plane, a cube, like, we've got a lot of options, but let's say we use a cube, because that's what we're doing so far. And I'm looking at this from the right side right now. Or, no, the front. And then you go and edit this. Imagine you're making more of a platformer kind of game. What's to stop you from using something like this as the base geometry for your level, right? Got something like this. Oops, I just wanted to grab the top part. There's nothing stopping you from bringing this into your game and using this as your ground, for example. And even adding in platforms. Grab this, shrink that down, expand it in the X. There you go, you got some platforms. So the fact that it's got some depth this way kind of sort of doesn't matter, as long as all of your objects are existing on the 0 axis this way. They're all going to interact with things fine. So you'll be using sort of a 3D physics system, potentially, to render what is effectively your 2D game, which is actually how the 2D system works internally. So that's step one. But the other thing you can do, which is quite cool, is if you do just use, say, the plane, which is just a flat thing, and we're just going to, rotate it sort of 90 degrees this way so that I can look at it well from, oops, rotate it 90 degrees this way. So then if you're in the front, oh, I'm hitting the wrong key. There we go. So that way, if you're in the front like this, you can also just be modifying this way. And all the tools in 3D work on your 2D object as well. So, right, so you can do this. And what's cool is you can read, even if you don't use this to display anything inside of Unity, what you can do is load in this mesh information, and you can find information about the coordinates of all these little vertice points. And yeah, I'm using the B key to select over here. And you can place things at these points to do whatever. You can use empty objects here in, where's the empty? Empty. You can use empty objects here in Blender, and these things will get imported into Unity as an empty game object, which then you can attach things to. You could name them something special over here in Blender, like put light here. And then you can have a script that finds all game objects with that name and actually puts a light there, for example. Whether you're working in 2D or 3D or anything like that, you can process all this information, which is kind of neat, I think. I don't know. I think that's kind of cool. And I think I might... There's a very real possibility that Next Legendary is going to be a 2D, more platformy kind of game, like something more action-oriented, which we haven't done before. And I may actually use Blender here to do my level design, even if it's a 2D game. Which would be kind of interesting, I think. All right, so what we're going to do is... I realize this was very fast. I do have some actual Blender tutorials on my channel, including some basic texture mapping and things. I would like to move on to talking about physics, but if anyone's got any questions about, you know, sort of Blender ideas, just fire away. Oh yes, you're right. There are extra faces on the ramp. That is absolutely true. So, what is it meant by that? Let's reopen our table here. So, if we look at this little thing that I've made. Whoops, that's not how I want to modify this. There we go. If we look at this bit that I've made, there are faces. This is what gets rendered. We can actually check face view, right? So we can see here, there's a face at the top and a face at the bottom. How do I center on an object with my camera? I'm trying to remember this. I know there's a way to do it. I can't remember the key. It's F in Unity. I can't remember what it is here. Anyway, so there's a face on the, you know, the top inside, the bottom outside. Here is another inside face, and there's another outside face right over here. If I can select it, there it is, right there. And then a little bit here. And these have to exist to A, be rendered, and B, be physically intact. But the little bits here, here, and here, and on the other side, don't need to exist at all. Because now what's happening is we're gluing in these pieces together as an array, you've got all these extra internal faces that don't do anything. That's extra data, it's extra information. The rendering engine's pretty good at culling this stuff, but it's still an extra step. It can certainly confuse the physics engine to no end as well. So what we're going to want to do is we're going to grab these faces here, we're going to select one, hit X to delete, and then say only delete the face. And that one there, and that one here, and then the ones on the opposite side as well. And I mean, there's a couple of different ways to do this a little faster, but this will work perfectly fine. We can actually even delete the extra edge over here, which I suppose if we're cleaning this up, we should probably do. This, we can switch to edge selected mode. This edge and this edge doesn't need to exist. So we can go and get rid of that. And that. And then if we pop out of edit mode and look over here, everything here should still look hunky-dory and fine. And in fact, it does. So we can resave this, and now we have a model that has a lot fewer faces, simpler geometry, but still works exquisitely well. Thank you. The comma key on numpad, well, I don't have one on the numpad. Could it just be period on numpad to center the camera? On selected object. There it is. The period key on the numpad centers the camera pivot on the object so you can loop around it. There we go. If you don't know, what I was talking about, which is really handy in Unity, is let's say here you want to rotate the view, but you're like, I want to rotate around this object over here, right? In my edit view, right? I want the camera to sort of rotate around this thing. Well, if you hit F, it'll actually rezoom the camera. Oh, the home is in a different place. It's actually a little bit misleading. Let's make a new object here as a dummy to show you. Let's make a dummy little sphere and move it over here. So now I want to rotate around this sphere, and it's like, well, is that really what I'm rotating around? If you hit F, it'll center the view on it, and that'll rotate around that. Oh, although in Unity, it'll only rotate around the object you have selected if you're in isometric mode. If you click on the little cube in the middle, you'll go into perspective mode, and now instead of rotating around the object, you actually just rotate the camera around itself. Sometimes this is what you want, but usually, and the big reason I work in isometric mode in Unity, is because usually I actually just want to orbit around the object. And that's true. You're not rotating the camera, you're orbiting around the object. And 99% of the time, this is actually what I want. So F in Unity, period on numpad in Blender. Da, 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 da. How do you know the correct face? Like the one that will actually be rendered. Also, how do we make simplified mesh for mesh colliders? Okay, well, in the example we were just working on, the way we knew the mesh that would be rendered is because, well, it was sort of obvious in this particular scenario. And I mean, maybe obvious to me, but I mean, it should be easy to imagine. These faces that we went and deleted, they were internal faces, right? Well, they're gone now, but these on the end pieces right over here. Now, technically, the way we have it now, it is going to be a little bit weird because we have this empty face on the end of our ramp. But that's because it's supposed to have an end cap. We're just ignoring that for now, right? So there will actually be a hole in our model right over here. But it makes sense for anything where there was a connecting bit, right? You're going to have right in here 2 faces that just face each other touching, which doesn't make any sense to have. So you remove them, so now you have sort of like this hollow kind of thing that if you really lined up right over here, it's going to be basically impossible to line up. Well, I guess I could do it this way, right? If we're looking forward, now if we zoom in over here, we'd technically be able to see straight through the model from one end to the other over here because it doesn't have start or end caps right now. And that's like the best way of simplifying that. In terms of making a simplified mesh for the physics system, what is being asked there? Typically with games, you have your visual mesh, which might be really high quality, you know, lots of extra little details, little sharp bits that stick out and poke out and look very cool. But the physics system, one, sometimes has an issue. If you've got an object that's sort of rubbing along a surface that's sort of like all jaggedy and pointy, things can get weird. Your objects can sort of bounce off each other in unexpected ways. So that's one thing. The second thing is a very complicated collision mesh is often way too demanding on the physics engine and can slow down the game. So that's why most of the time you have vastly simplified meshes that you will use for your collision. And what do we mean by that? If we pop over into Unity over here, when we import our table, one of the options we have is the option to generate a collider. So if we do that, it really actually makes almost no difference. The difference is, I was going to say, it's not even going to affect this bit over here. Or did it? Oh, it did actually. It adds in a mesh collider on all of our objects that get imported. Now, you don't actually have to use that automated tool. You could just manually add a mesh collider and then give it a mesh. Now, so what are colliders? Let's backtrack for a moment here. Unity has a physics engine. Let me make a little demo example over here. We're going to put down a plane, and I've got my sphere. I'm going to take the sphere up here. I'm going to add a rigid body to it. And then we're going to hit play. And because of the gravity, the ball will fall. There it is. I'm not lying. The ball will fall. Took a long time to process that. There we go. Now we're fine. The ball will fall. And in fact, if I take this ramp and I just angle it ever so slightly, say away from us, and we hit play, now the ball will fall and roll away from us. Physics, hooray! Why does it do that? Well, it does that because of two things. First of all, the fact that the ball has a rigid body, that means it's a physical object with mass that's affected by gravity. But more importantly, both the ball and the plane down here have a collider on them. And the colliders are what tell the physics system how things are supposed to, how they are physically present, what their bounds are, right? Like if I grab, I don't know, this can, how's the camera looking? If I grab this can, right? It has a collision mesh on the outside, which is where my finger can't go through. It's important to note that obviously in the real world, sort of the visuals of an object and the physicals of an object are basically the same. But there's no reason that has to be the case in a game. And so you need both of them defined. So the sphere has a mesh over here, the mesh filter and the mesh renderer are responsible for making the sphere visible, whereas the mesh, or the collider part of it is responsible for making it physical. We can especially see that on the plane. If I take this mesh collider and I just turn it off by removing that check mark right over here, and I hit play, now the plane is still visible, but it doesn't count as part of the physics engine. Okay? And there's no reason the two have to match. For example, let me turn on the mesh collider for the plane again. But on our sphere, I'm going to remove, and by the way, the collider is represented by these green lines. So I'm going to take on our sphere, I'm going to remove the sphere collider. And I'm instead going to put in a box collider. So now our sphere still looks like a sphere, but as far as the physics system is concerned, it is a box. And if we hit play, that will become very obvious because the sphere will not roll. It will just sort of be a box. If the box material was more slippery, it might still slide down the ramp, but it won't roll down the ramp. So, all this to come back to the idea, oh, right, the game's still running. To come back to the idea that you could have a very complicated and detailed visible mesh for your game world of some form, right? This happens a lot in racing games where you have like billboards and fences and the audience past the fence and little blades of grass and all this stuff. But you have that, and then you have another model on top of it that is not rendered, right? Imagine, and we could do this very easily. We take our table, which has a mesh collider. I could, if I wanted to, say double this up. And on the second table, I could turn off the mesh renderer. It's no longer visible in any way whatsoever. It doesn't render. And on the first table, I could leave the mesh renderer on, but disable the mesh collider. So now I have two copies of this table, one which will be affected by the physics system. This one here is physically present, but not visually present. This one here is visually present, but not physically present. And the idea is, on the second one, you have vastly more simple geometry. And there's two different approaches to doing this. Probably the simplest thing, though, let me just undo all this, because obviously this is not what we want. There we go. Probably the simplest thing, and what most people tend to do, is in their model, like they make their visual model, and then they go and make a series of a simpler version of that model, which can either be like handmade. Basically, you start with a new box, and then you carve it down to mostly fit the visual mesh. So it's mostly accurate, but much, much, much simpler. So the end result, you don't want it to look like your cars or balls or whatever it is clip through the visual terrain. You don't want it to look like you passing through any terrain, but you want to do that with the minimal amount of triangles possible to keep things dead simple. There are other tools that you can use to take an existing model and I think is it called Decimate? Decimate here in Unity or Blender, for example, and it just tries to strip away a lot of vertices and simplifies the model considerably. So these are sorts of approaches you might want to consider if you truly have a very complex form. In particular, for your thing itself, let's say you had a car, right? A car vehicle. 99% of the time, you do not need the collision box for your vehicle to be the actual vehicle itself. Usually, like a box, or maybe a couple of boxes, is going to be all you need. And it's especially important for the thing to be moving, the non-static object, to be as simple as possible when it comes to the collider for like really high-end performance. Also, again, if you have any sort of like little jagged bits that stick out, that can get like sort of snagged in very weird ways in the physics system that cause things to go crazy and weird and makes no sense. So that's the other incentive. Yeah, decimate means losing 1/10, so that works. It's literally using the term decimate in the appropriate way, although you can change the slider. But yeah, decimate doesn't mean destroy, it means to kill off 1/10. So there you go. And then there's the convex hull, which is a whole other thing. Now, for our world geometry, we wouldn't want that. But you'll notice for our mesh collider, there's this checkbox to set something to be convex. And if we tick this on, it'll make it look really weird here. Especially if I turn off the visuals. Actually, it doesn't make it look really weird. It makes it look literally like a box. What's going on there? Let me turn that around. Let me actually work with the ramp for this. I think that'll be an even better example. So the ramp has its mesh collider, and if we turn off the visuals, we can clearly see that the mesh collider, and this would be a good example of like, wow, simplifying this might be a really good idea. Might not be possible, but it might be nice because that's a lot of triangles in there. We've got that. If we turn on convex, things look really derpy with this. And what's going on? A convex hull, or convex collider, is one that is like rounded. It doesn't have any bits that like sort of sink in, right? Like if you go in like this, that's concave, right? A cave that you walk through in a mountain, a cave is a hole. So a concave mesh is one that has sort of a hole like this. A convex hull is one that doesn't have any at no point does it sink in. So even with the fist, it's a bit of a bad example because right here it looks like it caves in. But if you were actually treating this as a convex hull, you would have a triangle there to seal that in. And by doing that, you end up with a mesh that is A, often a lot simpler, but B, because of the way the physics engine works, this is not a million times, but significantly more optimized and faster to work with. Hey, Yabdat, thanks for the resub. Than a concave mesh, right? So a normal mesh, a concave mesh, is not as optimized. It tends to be more complicated as well. But more importantly, let's say I took this ramp here. All right? So I got this ramp. Let me turn on the visuals for it again. And let me go and I'm going to pull it upwards and give it a rigid body. So now it's affected by gravity and should collide. If I hit play, this mesh is going to fall through the table. All right, see that? We hit play, and it just falls through the universe. Why is that? Well, it's because in Unity, two convex meshes cannot collide with each other. And that's because it would be like apocalyptically difficult to calculate that sort of stuff in real time and be performant. But if I make this into a convex mesh, there has been some changes to this with Unity 5, but I don't think I'm lying to you. Now, it does hit the table. Again, this mesh doesn't actually match our visuals, but it does work. So anyway, that's sort of neither here nor there for this particular example. Undo, 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 undo. Okay, I think we're back in the right position. I think everything is the way it was. That's great. All right. Bum, 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 bum. Yabda, thank you for the resub. I think I said that. Nilefield, thank you very much for the resub. Yes, decimate is a Latin phrase. It was a Roman thing with the military. Really cool to see a tutorial one day how meshes and colliders work for objects that have damage modeling. Oh, yeah, so I think with damage modeling, I don't know if you would actually modify the collision mesh in real time. I mean, I suppose it would depend on exactly what kind of model it is. But like if it's a car game where, yeah, if you hit the right corner of your car, that corner gets sort of smashed, you lose your headlight, right? Well, whenever a collision happens in Unity, there's an on-collision enter. Yeah, an on-collision enter thing that you can like have as part of your script attached to an object. And in that information, it will give you information about the collision status itself. And that will include the exact location of that collision. So you can use that as a point to apply whatever. Maybe your car model is actually made up of a bunch of different components, and then you detect that like, oh, this is a collision in the front right quadrant, so I'm going to swap out the healthy headlight model with the one that looks damaged. You know, so you've cut up your car in multiple little bits ahead of time so that you can replace the roof or the right door or this or that or whatever with a damaged version of that particular submodel. Real-time deformation is possible, but man, that is a complicated topic and way beyond me for this sort of context. So yeah. Anyway, let's go and let's get some physics going on. We're gonna mess with that. So would you want to use convexing only when it doesn't mess up much of the collision box? Yeah, Eagle Fire, generally, yeah. I mean, if your object, you have to realize, if your object is really, really concave-y, you know, again, if it's sort of shaped like this, and the user will expect the collision to make sense in that if a pen gets dropped here, it doesn't just bounce here, right? If you set it to convex, it would bounce here. And if that would be inappropriate for the game, and a lot of times it's not because the collisions are too small or too far away, a lot of times that's not really noticeable or not a problem. You play games all the time where that is the case, where this would bounce right here. But if it's really important, then there's two solutions. If this object here has to be a rigid body that is dynamic and moves around, right? And has to collide off of other objects, then you can't have this be a convex mesh collider. But what you can do is you can use multiple other colliders which are convex to make it up. So what I can do is we can create this empty object over here. And what we're going to do is we're going to populate it with other objects. I'm going to imagine that this, we don't have it. I don't have a visual for it. But this empty object, imagine, if you will, that it looks like a C, right? Like this. And what we're going to do is we're not going to give it its own collision mesh. That would be bad. Instead, we're going to create sub-objects within it. And we'll just use, like, sure, cubes. We're going to use this And we are going to scale this down. And like that. And sort of like this. And then I'm going to duplicate this object, bring it over here, rotate it like this. And I'm going to duplicate this one, bring it down, rotate it like this. Right, I'm doing this very quickly. These cubes are all supposed to be inside of the game object here. And on all these cubes, I'm going to turn off the mesh render. They're not here to be visual. They're here merely to define the collision area using primitives. And then on your base game object, you would still have the rigid body. You would have the rigid body as well as your visuals here. Or, depending on how you want to do it, you could actually have your visual part of like, this is the graphics, right in there. So you have this one master game object that has the graphics and the actual collision elements defined as these primitive objects. And what's nice about this is this will indeed work. So if we, grab all these and, no, that's not what I want. This one here. Shrink that down. There we are. Let's give it a little twist. And it's over my table. And now if I hit play, boom, there you go. So you have this one object, this one C object, that is clearly concave, and yet it's still able to interact with the world because it's actually made up with a series of these primitive colliders, all linked together within one master object that has the rigid body component. So the rigid body component is on the master object here. So object with rigid body, right? Very cool. So this is like, that's cool. And the nice thing is, box colliders. Note that what we're using here is we're not using mesh colliders, right? Our ramp is a mesh collider. These cubes use a box collider. There's also, if we look up collider, and ignore all the ones with 2Ds, there's the box collider, a capsule collider, the mesh collider, the sphere collider, and then some others, ignore those. The mesh uses an actual mesh from something like Blender to define it. But the box, the capsule, and the sphere are these sort of subcases of the colliders that are calculated in engine. And because they take up, like, a box is very well defined, there's a million different optimizations you can make. DF2, brum, 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 thanks for the resub. You can make these optimizations for the box, sphere, and capsule colliders. That means they are much faster. You could make a mesh. You could make a mesh that is a cube like this, right? Or a rectangle in this case, or whatever. You can make a mesh that has this structure, and then you could use it as a mesh collider and set the convex flag on. It would not be quite as fast as this cube. I don't know what the difference in performance is, and it'll probably only come up if you have hundreds or thousands of objects, but there it is. So that's how that would be your solution. And this is also a great example of simplifying a design. This could be a really complicated, hey, White Raven Knight, thanks for the resub. And Phoenix Pick, thank you as well. This could be like a really cool spaceship or something like that, right? I mean, we're halfway to a Millennium Falcon. Whatever, you can imagine it, right? And the Millennium Falcon has all these little bits all over and the two prongs and all that. But rather than use its mesh as the collider, you would just use a series of these squares to define the collider around the Millennium Falcon, and you'd end up with something that runs a lot faster and can glide with different things and have that little concave bit at the front, right? It's got that slot in the front. And so things could pass through that slot if you do this, as opposed to being a convex mesh. Boom. All right. We should probably move on to the next bit. So simplifying design is awesome. Yeah, very good. Very fast, very easy, and tends to make things work the most. So I'm going to leave that in the project, but I'm just going to put that asleep. I'm just going to hide it so that it's there so you guys can reference things. Okay, so we got that. Let's go and add in our ball. Wow, the light makes it really shiny and sort of hard to see, but I guess that's okay. All right, game object. And for our ball, I'm just going to go and create a sphere as one of the built-in Unity objects over here. It's obviously very, very, very large here. So how big do we make it? Well, in Unity, your sphere here, if we look, clearly has a diameter of 1 unit. And as we talked about earlier, a pinball is 2.7 centimeters or 27 millimeters over here. So we will just shrink this down by 0. And we're doing diameter here. So 0.027. There we go. So now we have a pinball of the appropriate size. So We can zoom in here if we look at it from the side. All right, well, we're a little up in the air, but that's okay. And we're going to set it right at the top of our ramp over here. Now, because our ball here is a sphere collider, it's super simple, works well in the physics engine, can collide with anything, whether it's concave or convex, which works great. So it's got a rigid body. No, I'm lying to you. We're going to add a rigid body in here. It's got a rigid body, so if I hit play, this ball should hit the ramp and start rolling down. And it does. It's not rolling particularly fast, though. And why is that? I wonder if we'd actually have a better luck seeing things if I were going shaded wireframe. Yeah, there we go. That'll be a little easier to do that. Also, it came to a rest here. Why did it do that? Well, oh man, maybe it would be easier if I flipped this around. All right, let's do it. Rotate the table 180 degrees that way, and I'm going to put the camera back to whoops. What am I doing? Oh, I changed the wrong number. It's the Z I want to change. There we go. All right. So we're going to do that. So, and did I leave the sphere there? You're supposed to be here. Oh, right, of course, because I rotated everything. So then we'll hit play. It'll roll down the ramp and come to a stop over there. So there's a few things. First of all, our table is flat. Right? If I go and take this, let's stop this. Let's move the ball off the ramp and move it to over here. The ball just sits there because our table is flat and level. Now, the top part is off kilter, right? Because it looks cool. But the actual table surface is completely level. So what I could do is take my table and rotate it. But you know how much of a pain in the ass it would be then to try to place things all over here when you've got this rotated table? Oh, it would be awful. So we're not going to do that. Instead, we're going to rotate the world. So in your project settings, you've got an area here for physics. And one of the things you can do in this physics session is mess around with gravity. You can make gravity more powerful, you can make it lighter, you can do all kinds of different things, but you can also change the direction of the gravity, right? Right now, gravity is pointing straight down. Yeah, see, Joe says it. Solution, change gravity. It's easy. When the laws of physics are getting your way, screw them. Who cares about that? So, if we want, so a pinball table is tilted at 6.5 degrees typically. Depends. The older tables tend to be tipped less aggressively, and newer tables tend to be tipped a little bit more aggressively, and different things like that. But we're going to go with about 6.5 degrees of tilt. And if we take the oh, that's in radians? Trying to do the math on Google over here. Thank you. There we go. If we take the cosine of 6.5 degrees and multiply it by 9.81, we get 9.74. So our y-axis gravity is going to be reduced a tiny bit. Actually, I guess if we round, it'd be more accurate to say 747 over there. And then if we take the sine instead, we find out that we should have a force of gravity in the z direction of about 1.11. Is that going the right way? Let's find out. We'll hit play. Are we going towards the front or the back of the machine? The back of the machine. So we want a negative instead. So now gravity is tilted and the ball will roll to the front. Hey, that's awesome. We're still not quite where we want to be though. Now it'll correctly roll down here and go into our little hole. Ah, fantastic. We still have the issue of why is it rolling so slow? And there's a few different things that can happen. Someone might be tempted, let's make it heavier. Someone doesn't know Galileo. Heavy things do not drop faster. Heavy point, thanks for the resub. What was that quote with the world and lever again? Yeah, give me a lever long enough and a fulcrum strong enough and I will move the world. Something like that. That is very cool, yeah. So some people might want to make things heavier, right? And you could add more mass. Let's make this weigh 1,000 instead of 1. Mass, I think, is actually more like density in here, because doesn't it scale? I'm pretty sure it's more like... No, massive object. Interesting. In kilograms by default, but it's not really like that. It's not like that at all. It's more like if you have two objects that are colliding against each other, then the relative mass between the two of them matter. But here we can see it's done nothing for us. Well, there's still a few different reasons why that might be the case, but it's not doing much. If we do zoom in, the ball is rolling, which is nice to see, though. So it's not that. And obviously, two objects that are of different weight will fall at the exact same speed, you know, barring air density and things like that. So that's not the solution. So was it? Is it that the ground is too sticky? This can be a thing. You have all your objects that are physics in here have a material applied to them, a physics material. You don't normally have to mess with this because there's a default physics mat. And we can actually set this. If we look at physics over here, right? So edit physics, or was it edit project setting physics. There's a space for a default material. Now right now that is blank, but we can change that. If we create a material, and I don't know, we'll call it default. Or not material, sorry, my bad. We want to create a physic material. Default physic material. And then again, we go edit project settings, physics, and then just drag that in. This will now be the default physics material. If we take a look at any object, any collider, it's got space for a physics material. But if it doesn't have one, it'll use the default, which is now this. But when you create a new one, these defaults are exactly the same as before. Now we could mess with this. We could do weird things with friction or whatever, but that's not what's slowing down the ball either. I mean, it is going to have some play. It turns out what's actually slowing down this ball from rolling faster and faster and faster as it comes downhill. And this would be even more obvious, I would say, if we moved it to be on the top of the ramp here, right? This is a ramp. If we hit play, it should really gather up a lot of speed, but it's not. Is it drag? Well, it might be drag, but it's not that. Well, I mean, it's still in there. If we go back to edit, project settings, physics. Wait, it's not here? Oh, that's right, they changed it. I think I have to change it in code now, don't I? Hang on. They used to have a thing, but I think I have to change it in code now. Let me just find it. Yeah, max angular velocity. I don't think I can change it anywhere else. Value is usually changed in edit project setting physics, but it's not. Yeah, I think with 5 they removed it. So we're going to have to write a little script. Mounts, no. Yeah, okay. So there's a value in Unity, which is the maximum angular velocity, which is the maximum speed at which anything can spin. And it's set at a very reasonable default of around 7. And most of the time, it's fine. You wouldn't even notice that it's there. But here, we need the ball to be able to spin faster than that. What's happening is the ball is you know, starting to spin and hits that max speed and is not allowed to spin any faster than that. And we used to be able to change it in code, or in the editor, but we can't. I'm going to lose my window over here. Who dat? Silent Flame, thank you very much for the resub. And I swear there was another one right before that. Are You Badfish with the 2-year Twitch anniversary? Thank you very much. So let's write a little code. Let's, I don't know, add it to the sphere. It doesn't matter. Doesn't matter. It's just got to exist somewhere in our project. So let's create a new script called fix ball speed. Bum, bum, bum. Double click on that. Open it up. You can make the ball slide frictionless and be at 0 angle all the time. And a lot of pinball games do that. In a lot of pinball games, your ball doesn't actually roll. It actually just moves through just inertia. And actually, in a lot of physics games, don't have a real sort of physics engine, which is actually good because they can optimize a lot of things. And in a lot of physics engines, balls can't actually like go up. They can't actually lift off the table or anything. They're always like pinned down to the table and move around there. And it allows them to be a lot faster. It turns out the physics in these are really intense. Trying to get this game to run on a mobile engine might be kind of tricky. Punisher, hey, thanks for the resub. And Snevier, right before that, thank you as well. So what we're going to do is we're going to adjust in the physics engine dot max angular velocity. Oh, you set it for a rigid body instead. Maybe that's why they changed it. You don't set it globally. You have a maximum for each rigid body, which is actually a lot better probably. So we're instead going to say then, get component rigid body. See, I originally did all this in Unity 4. So max angular velocity. And we're going to set it to something big. Tell you what, let's literally set it to infinity. The ball is allowed to spin as quick as the ball wants to spin. Let's give this a test again and see what goes on here. Hit play. Now we're talking. Now the ball feels exactly right. It feels exactly right when it comes down here. It builds up speed and seems to move in exactly the way you would expect a real physical. It feels heavy, and it doesn't feel like it's being. It doesn't feel like it was a foam ball anymore that was being sort of stopped by air resistance. It is still stopping here, though. So why is that? All right, one problem at a time. So now it's good. We're no longer capping the angular velocity, and that seems to have fixed most of the ball behavior. But why does it stop right over here? So again, these are things you're not going to tend to notice in most of your games. So there's a couple of different reasons it might stop here. But one of the things that the game engine does is it has various sleep thresholds and things like that. If ever a physics object basically comes to rest, it will then fall asleep and no longer be processed by the physics engine until something happens to it. And the game is still running. I could take my ball and just move it up over here, and that will be enough to wake it up. And then it's fine. And then it sort of comes to sleep again there, which is great. Again, this ball really can't move. Unless I nudge the table or something, there's literally nothing it should do, so it should be asleep. And that's a good thing for most physics system, but in the pinball world, it sort of screws you up. Or other games that you make that are like highly physics dependent, you don't want your ball to fall asleep here. So can we do something about that? Absolutely. In fact, let's run this in fixed update, because this is literally within the physics engine. So the physics engine runs once per fixed update. Fixed update runs when the physics engine runs a tick, whereas update runs once per visual frame. They're not the same. With your rigid body, and I guess for the sake of speed, what I should probably do is something like rigid body, my rigid body. Unity 5 does a pretty good job of caching this stuff now, but it's still probably better in our case if we go and grab this completely. We'll do that, and then do that. And then here, wake up. So we can tell our ball that it's never allowed to fall asleep because we're going to try to wake it up every single frame. Is this going to fix all our problems? No. But it's going to get us part of the way there. Huh? There you go. And actually, after it hits this corner, it keeps rolling. It will never fall asleep. It may come to a rest because of friction and different things, certainly. It may not be visually moving anymore, but will not actually sleep. Now, that's one way of doing it. We could, alternatively, tweak the settings in the physics engine over here and just lower the sleep threshold to something very, very, very tiny. So let's say we did this instead. So very tiny amount, and let's remove this piece of code. Things can now technically fall asleep, although they're very unlikely to do so. But I think that, and indeed, the ball didn't fall asleep on this go. But it did, no, it didn't fall asleep there. But I don't know if that's really what we want, because I can still see all kinds of cases where the ball might accidentally fall asleep. And again, that's really good in a normal game. We played a lot of games where like stuff just sort of, goes into sort of a static form, but I don't think that's good for this. So I'm actually going to go ahead and leave the old number here. Can I right click and reset it to default? No. But what was it, like 0.05? So we're going to leave the sleep threshold where it is. We're going to make sure the ball never falls asleep. Although the fact that it keeps moving down here makes me think that probably it doesn't have any drag, and I think it needs some. It's got a bit of angular drag, which is okay. I'm going to give it just the tiniest little bit of actual drag as well. Now, your drag here will affect your maximum speed of your ball. So you want it relatively small. But that will cause the ball to eventually come to a rest over here. It probably needs a little bit more drag, actually. Because it feels like it's rolling for a little bit too long. But it is going to come to a stop. And I don't know. You know what? Maybe this is perfectly reasonable. So we got that. Now, next bit. Next bit. When the ball hits over here, it just thumps to a complete stop. It should probably bounce a little more, shouldn't it? I think it should. So how do we change how bouncy the ball is? Because, right, it's hitting right over here. Let's zoom in again. Hit play. Thump. That's no good. We need to have it a little bit of a bounce. And what we can do in our physics material, that's where we change the bounciness of things. Now, what I don't think we want to do is change the bounciness of the default material. Because Almost everything in the game world here is going to be made out of a particular material, but we might want the ball to be in a slightly different one. I don't know. Most of the table is going to be, really, you're going to talk about 3 materials. I think that is mostly true, actually. You've got the metal of the ball itself. Then you've got the tabletop surface. Then you mostly have rubberized surfaces. Everything else the ball hits is mostly going to have like a little rubber coating. Although sometimes there might be the equivalent of the tabletop surface, like on the ramps or whatever, right? Just basically a smooth, relatively tough surface for the ramps or the back face of the table or anything like that. So really there's 3 materials involved. And honestly, I'm not sure the ball needs a separate material. I think we can assume that there's a relatively hard, rigid material, and then there's a rubbery material, and that's probably all we need. So we can probably give the default physics material a little bit of a bounce, because honestly, the harder a material is, the better it bounces. If you've ever had a marble, which is made out of glass, which is extremely hard and rigid, and you drop it on a concrete surface, it bounces really, really, really good. We interpret relatively soft material like rubber as being very bouncy, but that's not necessarily accurate. So I think we'd want to give everything in the game a little bit of bounciness, and it just uses an average. Let's say we put it 0.5 bounciness. Are we going to be satisfied with that? Okay, it still didn't bounce off, but it should have, right? Literally everything in the world has a certain amount of bounciness. So why didn't the ball bounce right here? That's because in our project settings, physics, we have this bounce threshold. This is how much strength it's got to hit for us to bother calculating a bounce at all. Otherwise, it just gets soaked in. Well, we probably want a relatively low number here because we want this is supposed to be a super accurate physics simulation. There we go. So that looked pretty good, although what's this rattling going on? Well, this ball is bouncing up and down and things in very awkward ways right now. In fact, constantly bouncing off the table surface. So our bounce threshold might not be quite right. It's a combination of bounce threshold plus the bounciness of a surface. What if we just set it to 1? Oh, now that looks much better. No more bouncy jitteriness at all, but the impact here, that feels pretty good. Looks like it bounced a little sooner, but I think it's actually a frame rate thing. Yeah, I think it was calculating that it was going through on the bounce over there. I'm just going to look at it over here. Now, see, that feels pretty nice. Let's give it a little bit lower threshold, though, because I think it could probably use a bounce over there. So you're trying to find the sweet spot where the physics system doesn't go berserk, but it feels pretty good. All right, we're getting there. Bounciness is a much more sciencey sounding name. Coefficient of restitution. Yeah, but bounciness is awesome. Bounciness has ness in it, therefore it's really sciencey. All right, so we got that. Let's get to the next thing that's going to completely break this and try to insert a flipper. I'm not going to explain what I'm doing here. I'm just going to very quickly draw a flipper because we're in a bit of a time crunch. But I'm going to start with let's say a circle over here. I'm going to go into edit mode. I'm going to grab this part, get rid of half of it, grab this part. I'm going to move it in the X direction over here. Something like this mount. Then I'm going to go and apply a mirror modifier. Boop. Then I'm going to apply the mirror modifier. So the modifier is gone, but the change is permanent. Then I'm going to box select these two, hit F to merge them together, or to build a face. Box select those two, build a face. Well, technically, I'm just building an edge. Then I'm going to grab everything and extrude it upwards in the Z direction. Bam. And then with everything at the top selected, I'm going to hit F to build a face there. And with everything at the bottom selected, I hit F to build a face there. And we have a flipper. This is an old-timey flipper where it's the same size on both. We could make it a new-timey flipper by shrinking down one side like that. Boom! New-timey flip. Oops. Hold on. Undo. Undo. We want to shrink. I'm going to hit Shift-Z so we shrink in all the directions except the Z direction. Voila. I'm going to grab this. I'm going to tell it is smooth shaded. And then I'm going to put an edge split on there, which is going to look, I think, pretty right. We're getting a little funky reflection kind of thing going on in Unity or Blender, but we're all right. And then technically, what we do is duplicate this, shrink this down, and then scale it positively in the Z until it pokes out. And then actually take this thing and scale it in the Z only like that, and then bring it up in the Z only like this. Voila. And so this one is going to get called flipper.rubber. And this is going to be called, it's the flipper.plastic. Bam. So I'm going to save this and call it flipper. Save. And go into Unity. It's completely the wrong size and everything, but that's okay. I'm actually going to create an empty game object here. And I'm going to throw the flipper inside of that. And the nice thing about this is then I can take this flipper object, which is massive, and scale it down to a much more reasonable amount. But within the parent object, and the parent object itself, which needs to get changed to a height where it's above the table. Parent object itself has a scale of 1. So you change the graphics without changing the parent object, which is awesome. So this would be, I guess, the left flipper over here. Let's give it some color, because right now it's really, really, really hard to see. So I'm going to create a material. I'm going to call one white rubber. And then I'm going to have another material. What am I looking for? Right here, which is going to be called red plastic. And I'm just going to make this red. And then on the flipper, I'm going to say that the plastic part is the red plastic. Oh, my normals aren't right. Oh, that's why it's looking stupid. Look at this. Ah! It's because Unity or Blender, because I started with a flat object, didn't know which side of the triangles are supposed to be inside versus outside. So we can fix that. We're going to grab all this. Can I do it in this mode? I think I got to be inside. And what I want to do is flip normals. Boom. And over here as well, we're going to flip normals. Save that. Now it is the right way around. No, it's not. It's still confused. We need to, there's a tool to fix. Make normals consistent. Control N. That's the one I'm thinking of. Make normals consistent. There we go. Half our normals were facing in when they weren't supposed to. Now, there we go. Excellent. So we got that. Did our rubber get the white rubber? There we are. So we've got that. We should probably give some sort of, I'm going to give a color to the table itself. We might get a texture going, but let's just call this tabletop. Let's give it a slightly beigey, browny color, because it's, I don't know, wood. And drop that on table over here. There we go. Now it's a lot easier to see things that they're different colors. Cool. All right. I'm going to take this is actually the flipper.left, like that. And we're going to bring it down. Down, 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 down. There we go. So we have a flipper here. And obviously, it needs some sort of hitbox, right? Because right now our ball can go directly through our flipper. We can take our ball and go home. Should call this ball instead of sphere. And take this ball, make sure we're looking directly straight down. I'm going to grab it, bring it right over here so that we can see what's going on. And I'm going to bring it down to the tabletop, just like that. And if I hit play, it's going to go right through our flipper, which is fine. So what we need is we need some sort of collision box on this. And I guess the easiest thing to do is to go to the flipper and say, hey, Unity, could you generate a collider for me and apply that? So now, if we look, we've got mesh colliders. And if we hit play, it'll hit. Okay, great. Now, currently, we have a mesh collider both on the rubber bit on the outside and also on the inner plastic bit. Well, the inner plastic bit doesn't need a collider because nothing will ever touch it. So we can remove it, therefore making things run a little bit faster. So only the outside rubber bit has a collider. So we've got that. That's good. The ball can hit it. Cool. Clearly, we're going to need a more bouncy material for that. So I'm going to create a physics material for rubber physics material. And we're going to give it a bounciness of like 1 on there. I'm going to apply that to the mesh collider that's on the rubber. So now, we might not notice it here, but technically it's a bit more bouncy. I mean, the ball's pretty close there and doesn't have much speed. We'll bring it out over here. Well, clearly we still have to mess with our bounciness because it's dying too quick. Physics. I think at 0.1 we were still getting weird jitter, weren't we? Yeah. 2.5 maybe? Okay, there's a couple other things we can do for that. I think our default physics material, I'm actually going to reduce its bounciness to like... Actually, I might bring it down to 0, or make the tabletop completely unbouncy. Bring it down to a fraction. There we go. Now, the reason you're not seeing the ball collide is because the physics system, the time ticks, is a little too big for the speed. We're going to tune that in a moment. But there we go. That feels about right. And we're no longer getting the jitteriness. Yeah, I like that. I think that feels better. Okay. So we got that. That's great. But what's a flipper that doesn't do anything? So how do we get the flipper to flip? Well, what's our time? Oh, God, I'm going on way too long. That's okay. How do we get our flipper to flip? Well, first of all, it needs to be something that's physics enabled. If it's going to move in the physics world, which means it's a rigid body. Now, if I just give it a rigid body, it's like right away you're like, right. A few things. First of all, it's affected by gravity, so it's going down. It's falling through the world, which should give you a hint of, right, the only reason it would fall through the world is because it is set to be concave by default. And this is clearly... There's nothing concave about this, so we can make it convex, which means that it'll no longer fall through the world. It can interact with other things that are collision meshes, and it makes it more fast and optimal for the game. So there we go. So now we drop onto the surface, and things look derpy. I mean, obviously this thing shouldn't move, right? So how does a flipper work? Well, clearly it's anchored right over here. It's supposed to be static over here. It's going to be on a hinge. Perhaps a joint. There you go. So we got a few options for joints. We've got just, say, a hinge joint, which we can do. And then it needs an anchor somewhere. We should be able to visualize the anchor. That's connected anchor. Sorry. Here we go. It's a little hard to see. See, there's a little arrow over here. It shows you where the anchor point is. And I think what might be good, I'm going to put in, as a little placeholder here, put an empty game object over here. This is going to be called, I'm just going to call it hinge so we can visualize things. And I'm going to put this at the 0, 0, 0 point. Actually, let me take this back. I'm going to put in a capsule, which is going to be way smaller because it's huge right now. Yeah. 0.1, 0.1, and 0.1. And even smaller than this. 0.01, 0.01. Okay, so now I can see this object. And this capsule object is at the 001 point of the flipper parent. So then what I'm going to do is I'm going to take the flipper graphic and move it such that the hinge looks like it's about the right place. Now that was just a visual placeholder. I'm going to disable that capsule. We're not using it. It was just to be able to picture things. And then I'm going to take the parent object and move it so that it looks about right, which is great. Now, though, the hinge should be at exactly the right point to just hinge around there. So let's go and give that a test. And we're going to say your axis for the hinge is going to be the y-axis. Right? Y-axis in Unity goes straight up, so we want it to hinge around there. So if we hit play, now we've got it. So now that's working well. If we took this thing and moved it up, it would go like all the way to hang down. Right? The only reason it wasn't going all the way down is because it's literally hitting the thingy on the back. Boop. Okay. Nah. All right. So that's all good and lovely. But that's still not a flipper. Flipper, it needs to flip. I've tried like a billion different ways to make a good flipper. You know, applying like motor forces, applying torque directly for the physics engine, and a lot of them were really tricksy and not great. It turns out, in all my experimentation, the best way seems to be to set a spring. So if you've got a spring, you get a certain force. I don't even remember where to start with this. Try with 100, see what happens. That is insufficient. Oh, use spring. I always forget that. Click the check mark. There we go. Let's bring that down a bit so it's a little bit more obvious what's going on. There we are. And even if I weaken it even more, so as soon as I hit play, it bobs down a little bit, and the spring tries to bring it back up. There you go. So you've got that sense, right? It's trying to stay in this position, and then springing back up. What about an animation? Would be a terrible option, because the whole thing with this isn't about getting the object to just move in any sort of visible way. It's to get the object to move in a way that the physics engine understand what's going on. Because what's going to happen when you activate a flipper, it moves from the down position to the up position in a fraction of a second. And the physics engine needs to be aware of that entire movement in a way that it's comfortable calculating all those sub-moves, and which is going to occur through a combination of different ways of collision detection, improving the joint iterations, and probably improving the physics time step as well. But you can meet it part way by keeping that movement as simple and as calculated within the physics engine as possible, and using the spring is a good way of doing that. The other thing you can do with the spring is you can give it a target position. So let's say we give it a target position of 15 degrees. So now when I hit play, it springs there. Or actually, while it's playing, let's say, so it springs there, and let's give it another target position of negative 15 degrees. You see what's going on here? This is released. This is when you push the button. It springs forward. I've really found out that the easiest way, the best way in my experimentation to get the physics system to work right is to get that to sprung with the spring. I've played with motors, using limits. Actually, you probably still want to put in limits, because one of the things that shouldn't happen is when the ball hits it, it shouldn't actually be able to go down, really. That doesn't make much of a sense. So you probably still want a limit. You want to say there's a maximum of, say, 15. So now it literally can't go past that, although you could still arrange a certain bounciness. There you go. Now it's nice and fixed. Because internally, mechanically in the pinball machine, there's an actual physical stop there, so that it stops the flipper from moving back anymore. But we can still go and say, sprung forward. Oops! But we actually have to set a positive limit here of, say, let's say we set minus 25 that way. There we go. So now, sprung down, sprung up. Good. Now, you don't want a strength of 1. That's obviously no good, and it will become very obvious once we get a ball on here that 1 is not strong enough. The flippers actually move very quickly. Technically, they move back more weakly than they move forward. Because when they get pulled forward, it's actually an electromagnet that fires. It's a solenoid that pulls it forward, and it's very fast. And the way it pulls back is the solenoid turns off, and it's an actual physical spring that pops it back into position. And the popping back is technically supposed to be a little slower and weaker, which you could simulate by messing around with these strengths. Like maybe springing up is strength 100 spring, but coming back down is maybe only strength 10 spring. May not actually be required in your game. And of course, you may not be making a pinball game. I'm trying to like demonstrate certain things, but imagine like some sort of platformer that uses these things to fling up. Now, on a platformer, you may not actually want to use an actual physics thing. You could fake it. You could have a code that just, you know, oh, you hit this button and the character is within a certain area, therefore just apply a certain force to the character. Done. But obviously, we need something a little bit more accurate over here. So let's give it a little script here. We're going to call this the flipper script. And what it's going to do is it's going to track if we're hitting a button or not. So what I'm going to do is I'm going to set a Boolean that says is active, which starts off as false. Okay? And in our update, so update runs every frame, fixed update runs every tick of the physics engine. If you want to move anything physically, do it in the fixed update. But if you want to interact with the screen, or more importantly, if you want to interact with the input, you probably want to do it in update. Technically, get key. So let's say we're using shift to flick things. Get key, key code.left shift works perfectly fine in fixed update because it checks it at the time. But get key down, if you try to use get key down or get key up in your code, it's not going to be great. So it might be worth doing in two separate things. And what you could do is you could do something like that. So if left shift was just pushed down, we set is active. Is active? Is active is fine. It's is enabled. Then yeah, we set it to true. And else if input dot get key up key code dot left shift. Just for now, obviously we'd have to generalize this for both sides. Say is active is equal to false. So you do something like this, and then in void fixed update, which is where the physics engine runs, then you would do something like if is active blah. In fact, we might want to check, rather than do this, we might have a separate Boolean that says become active. Right? Or, you know what might be better? Let's change this around. Fixed update. Let's just do this. In our fixed update, we check to see if the key is being held down. And then, if the left key is being held down and is active is equal to false, we say become active. Else, if the key is false, if the key is not being held down and is active equals true, stop being active. That might be the best way of handling it, so that we only set things in at a particular time. And then in this code, obviously, we set that to be true, and here we set it to be false. But what else are we going to do in here? Well, we have a hinge joint. Hinge joint, my joint, which we're going to grab here. My joint is equal to get component hinge joint. So we can start doing things with it. And what do we want to do with it? Well, when we become active, as we were doing in our test, we know we want to set the spring's behavior to do something. Well, you can't just, well, you can sort of access things. I think this is one of the ones you're not supposed to change. Well, let's find out. We set it to target position. We're going to set it to 25. I don't know if you can set this directly. And over here, when it's not active, we set it to -15, which is the default. Yeah, I was going to say, you can't edit it directly. It's like a vector. So instead, what we're going to have to do is, we're going to have to say, I have a joint spring, which is my joint.spring. We grab a copy of it there. We set its parameters. And then we say, my joint.spring is equal to this new spring. Copy. Paste. There we go. -15. All right, let's see what this does. It should compile. Should be able to hit play. Oh, my limits didn't get saved. I'm like, what the hell's going on here? There you go. It's because my limit was set wrong. Let's try this again. You're there. Oh, I've got my logic inverted, though. Because this is the -15, and this is the +25 version when it's active. Obviously, hard coding is bad. We'd want to put in some parameters we can tweak. There we go. Boing, boing. Okay, right away you can see it's working, but it's way too weak, right? Let's change our strength to 10 and see how that does. Boom. Oh, now we got a little bit of motion going on. Probably still not quite strong enough. I wouldn't go crazy, but let's try 50. Oops, I went a little too early. And again, I'm trying. I should actually get my little bit over here, because the problem is it's kind of hard to time it. That might not be strong enough. Let me go and get, it'll be a lot easier on me if I get a cube, which needs to be shrunk considerably, and raised up. And then rotated. And brought in somewhere around here. And then grab the ball and bring it here. Oh, my cube's way too high up. Cube. Shrimp. There we go. There, that'll be a lot better, because now we can get the ball to roll onto the flipper. Yeah, all right, which is still too weak. No problem. So we tuned it up. Oh! Aha! It's going to run into the same problem as the ball. So I'm going to be like, let me do crazy. Let me set it to 5,000 spring strength. And I'm going to hit go, and it's still super weak sauce. Actually, although the spring is still so strong that the object is going slightly crazy when I release it. What's going on? Well, it's the same thing as the ball. We're hitting into the limit of our maximum angular velocity. So we have to tell our flipper that it's also able to flip as fast as it damn well pleases. And with that note, let me bring this speed way down again. Let's try 50 again. That should be quite a bit faster. Boom! Not still quite there. But definitely stronger. Let's try 500. Boom! I think something still might be missing. Still not hitting with the strength that I'm looking for. Why is that? It's definitely missing something else. I'm trying to remember, but we actually are out of time. And I didn't do reflections yet. So I'm going to go and set this aside for a bit. We're going to show you some real quick, real-time reflections. So, the way you do reflections in Unity with the physics-based materials is quite cool. Let's go to shaded mode over here. So you can do it quite simply. First, by creating new material. Let's make our ball material, right? So this is shiny metal. It could be the ball mass, the flipper too low. It actually might literally be a question of making the flipper somewhat more massive, because it might be losing some of its inertia. Oh, that was something. Hold on. Yeah, something else. I mean, I could make the ball lighter. I don't feel like that's the right approach, though. Although, I guess in the system, it is considering to be like a kilogram. So we can make it something like 10 grams at this point. No, there's another cap. It might be... It's something else. It might actually be... There's a total velocity limit that it might be hitting. There's something else. Just out of curiosity, though. If we went and reduced the sleep threshold, so by default, or not the sleep threshold, that's not what I meant. It's under time. Project settings, time. So this fixed time step determines how often the physics engine runs, and by default, it runs at 50 times per second. Let's change it to 100 times per second, just out of curiosity. There we go. And at a certain point, you have to do that. In this kind of game, so that was actually completely realistic. You want to wait until it's at the end of the flipper and then give it a good fling. By having higher fidelity in the time step, you get a lot more accuracy. Out of curiosity, if I put it back down to this, so it runs 50 times a second instead of 100, but in the physics engine, I increase the solver iteration count, which is specifically for joints. If I double that, no, that doesn't solve it. So you just need a little bit more CPU power just thrown at it so that it's properly calculating things. So there you go. With a fixed time step of 100 times a second, that is very good. That's very much what we're looking for. And then it becomes a question of messing around with the angle over here more than anything else, like the angle that the flipper is flipping at, and other things going on. And then you end up being able to shoot it in the right way. You also probably will end up having to fix around a little bit with the friction of the rubber against the ball to give it just the exact right amount of sort of catch. But that's tiny little fine tuning. But there you go. So a combination of removing the angular momentum limit, tweaking the time step, using the right kind of joint over here. If you try to apply this directly with force, it can be very tricksy. I will tell you one thing, though. This works a hell of a lot better and a lot faster in Unity 5 than it ever did before because of the new physics engine. Boom! Jeremy Clarkson solution. More power. And then you try to run this on mobile, and it actually turns out to work surprisingly well. Although you do certainly start to hit some limitations. Hey, Red Serpent, thanks for resub. Okay, let's work on reflections over here. So we've got our ball. It's a great little ball. And we've got the shiny metal material, so we're going to apply that to our ball. And how do we actually make it shiny? Well, you make it metallic. Metallic objects are shiny. Now, the problem is right now, it is shiny, but it's only reflecting our background, which I just realized, because of the way the scene got created in 2D mode, does not have a pretty little skybox. So can we get that in here so that I can correctly show you the wrong way? There we go. Default skybox. So now we have a skybox in here, which is good and lovely. If we look at our ball, it's still not I thought it would show the skybox. Reflection source skybox. Let's make it a little higher, although it shouldn't really matter for this. Build it quickly. Is it automatically assuming a reflection probe? I guess it is making one automatically. There we go. Now we're in the status that I was expecting. So now we have a ball, and it is shiny. But what is it reflecting? It's reflecting the sky, which would make perfect sense if the ball were over here. If the ball were over here, and we've got a lovely sky in the background, and you look at the ball, and you're like, yep, it is totally reflecting the sky and the sun. That's great. Yeah, so I can correctly show you the wrong way. Yes, exactly. That's how we learn. But if I have it in here, all of a sudden it doesn't make any sense anymore. Because, like, okay, well, there's still some sky, but shouldn't you be reflecting this stuff? But it's not. So why is that? Well, it's because reflections are actually insanely, like, hard to compute. They take a lot of horsepower to compute. And so whenever you have a shiny object, you have to sort of kind of tell the shiny object what it's reflecting. Basically, the way it works is there is a map of your environment. You can imagine it like a cube. You've got a cube somewhere, and you're sitting inside the cube, and when you look up and you look at the sky, well, that view from the top of the sky is what is at the top of the cube. And if you look down at the ground, that view from the ground is what is at the bottom of the cube, and so on and so forth. And that cube map is what gets used for reflections. And by default, the cube map simply includes the skybox. So how do you tell it to use more than that? Well, that's where reflection probes come in. So what we're going to do is we're going to create a new empty over here, and I'll put it roughly at the same position as the ball. Okay, roughly. And we'll add a reflection probe. Now, it's a big thing. It's only going to be there when you have it selected. When you don't have it selected, you get this little preview-y thingy. But reflection probe. Boom. What a reflection probe does is it gives you a new spot from which to calculate a reflection. Okay? There's basically a camera right in the middle of this reflection probe that takes a picture up, down, left, right, forward, backwards. And then anything that's within this radius, well, it's not the radius, it's actually this cube. Anything within this cube will use that. And we don't actually have to have something quite this big. We can actually have something quite small, in fact. And where are you physically located? Bring you in from the side. Let me get your wireframe here so I can see this better. Can I change the size of the goddamn preview over the reflection probe? I don't know, because it's like rather large and unwieldy, this preview. It's not the clipping plane, is it? Can I, if I tweak this, would it change? No. I mean, and that's just the preview. It's just, if I go and turn off the reflection probe gizmo, no, the other bit. Really? People are saying gizmo size. It's not that. Is it? There's somewhere over here? Gizmos drop down. I'm here. Yeah, I can change the box, but I can't change the, oh, the scale on the game object. That's an interesting point. Yeah, okay. Thank you. This is purely a visual thing. In the editor. It has no game impact whatsoever. There we go. Now I can get the reflection probe to not look dumb anymore. Okay. So what's going to happen is wherever the reflection probe is located, okay, that is going to be the center point at which this camera is for calculating reflections. Okay, and you can put it anywhere. And then anything that's inside of this box is going to use this reflection probe. You can actually see it as I move it. Some of the things are changing a little bit because they are using this reflection. And actually, take a look at our ball, right? If the ball is outside the reflection probe, it is simply reflecting the sky. But then as soon as it touches the edge, right there, just touching the edge of the reflection probe, it turns black. Why is that? Well, it's because this reflection probe hasn't been activated yet. We could bake it. Now it's got some environmental information. And actually, that's what the circle, this view is. It's a preview of what it's supposed to see. And by default, it only includes things that are static because you bake this in the editor. So let's take our table. Our table's obviously never going to change, right? Our table, the ramp, the skirt, those are all never going to change. So we're going to flag these as being static. They're never supposed to change at all. So now if we take a look at a reflection probe and we bake it again, it should correctly include, and you can see it in the preview here, it now correctly includes the table and all that in its reflection. And anything that's within this reflection probe area will use that information. Ball should be using it. It's not being very obvious that it's there. There you go. Increase the smoothness. There we go. Because it was too abrasive. If we bring it to mostly here, 97% smooth. Now it's super nice and shiny. So then again, to the reflection probe, we move it out. The ball should Why is the ball still like that? There we go. I was gonna say it shouldn't be. Okay, just had to wake up again. And if we move it in here, it turns black. If we bake this, now it's good. If we go here, there we go. Okay, there we go. I don't know why it was doing that. So now, when the ball is in there, it's using the reflection information. When it's not, it's just using the sky. So, real-time reflections are kind of slow because you have to take this camera that's in this reflection probe and take like 6 screenshots basically in each direction. So, you can bake it, but then it doesn't change. But how do you get this information in real time? Because here's what you find out, right? Let's say I take this cube. Actually, let me take the reflection probe. I'm going to move it right on top of the ball. I'm going to bake. Make sure everything's good. Excellent. Then I'm going to change the cube, and I'm going to have it use the, say, the red plastic material. Well, in the reflection map, the cube is still white. Actually, sorry, this cube was never set to static, so it wasn't in the reflection probe at all. Let me bake again. Now there's a red cube, and then let me take my cube and decide, no, that material's bad. Let me change it to the white rubber material. Now the cube is white, but it still shows up as red in the reflection. So then I have to rebake this. That might be good. That might be terrible, right? It's actually very optimal to bake it all ahead of time. But the important thing is this. When the ball moves around, let's say we take the reflection probe and put it on top of our ball. So wherever the ball moves, the reflection probe will move as well. And we'll get everything centered. And that's quite good. And again, we'll bake it again. The problem is this. As the ball moves, the reflection doesn't update. Which clearly it should. So what we need to do is we need to get the reflection probe to update itself every single frame, which we can do. So the default for reflection is baked, which means you hit the bake button and it runs it in the editor. You can also say real time, although by default, the real time will run on awake. So when the reflection probe wakes up at the start of the program, then it will take its screenshot and go from there. That saves you time during editing, although it means there's a longer startup time for the program. But that's still not what we want. It's like, great, so I'll hit play and it'll update itself, but it still doesn't update itself on the fly. So as, the ball is moving around, the reflection still looks kind of wrong, right? And that becomes really obvious if I go and set it, say, we'll put the ball way up here. And I think I will now be following the ball. And I hit play. It will update its reflection map, which is great, but as it moves... Hello, editor view. Why'd you go all derp? That was weird. Oh, maybe because I was actually linked to the wrong thing. Oh no, I moved the wrong thing. I moved the reflection probe and not the ball. Sorry, let me try that again. move you up here. Hit play. So it updates its reflection map at the start, but by the time it comes down here, it's no longer, it's not showing me the box or the flipper in the reflection. So we want it to update every frame, which you can do. Because instead of refresh made on awake, you can say, I want you to refresh every single frame. Now, at this point, you're really starting to stress your computer a little bit, but it's not too bad because this is a relatively small reflection probe, not going to get used by very many things. And our resolution on it is very low right now, so it's actually a very quick operation. And I think for the ball, it's going to be fine. I don't think the ball needs to be any more precise than that. Hell, it may not even need this level of precision. We might be fine with like 32-bit precision on this. Very fuzzy, but it might be sufficient. Now, by default with every frame, it still probably won't do exactly what you want. Yeah, the flipper isn't static, you're right, but because this is a real time, it should show me the flipper. Because it's happening at real time. So it should show me the flipper if things are actually being updated. It's just the baked version will never show you something that is dynamic, that is unstatic. But the real time one should. So we've got that. Let's hit play and see what happens. And hit play, I'm going to bring up the flipper right away. Oh, let me bring the ball a little closer so it doesn't keep rolling as much. There we go. And if we look at the how am I going to do this? I guess I can hit pause. There we go. That'll work. So start that up, hit pause, and zoom in here. And we can see, just barely, there's a hint of red over there. It's got the flipper in the reflection. So that is working. It's grabbing the flipper at real time, at runtime. And actually, the reflections look pretty damn good and convincing if you keep an eye on this. It's looking mostly all right. It still doesn't actually update in full real time. Because, by default, even every frame, this time slicing of all faces at once doesn't actually do what you think. Because what it does is it renders all the frames sort of on the go, and then the next frame, it renders the next MIP level, and so on and so forth. And in practice, it takes something like 6 frames, 9 frames. See below. Oh, it's got it described somewhere, but I think it takes something like 6 frames to actually render the entire update. So it's not actually running in every frame. If you go no time slicing, then it's basically not farming things out to a separate thread. It's doing the entire processing every single frame, which might be slow, or it might be super fast. But if we look like down here, we actually get really good behavior. The box looks a little bit weird because it's getting clipped because of the near clipping plane, which we probably want to bring down to a very small amount. And it doesn't have to render things very far. It'll never have to render things more than, say, 1 meter away, for example. There we go. Now that looks a lot better. Look at the reflection happening in real time. I hope that shows up properly for you guys. Come on. Try not to actually fling the ball away. There we go. All right. Nice little real-time reflections. And this is like, I'm looking quite close here. You would not actually be looking at this from this close. But you have it running, and the frame rate should be good. I mean, for me, it'll probably just be locked to my normal 85, 90 frames per second, which is the refresh rate of the monitor. I could go and disable the VSync. But if I did that, what's going to happen is the stream's going to die, because it's actually going to explode my video card. But I'm willing to bet we'd probably get like 1,000 frames per second doing this. Obviously, a very simple screen, but you've got real-time physics, or real-time reflections over there. You've got very fast physics. You may have noticed that the ball does occasionally like a weird little spin thing here. It keeps spinning quite a bit more than you might expect. And that's a combination of the tabletop friction plus the angular drag. So you may want to have the ball not sort of keep its spin too much. You definitely want to keep that going in these games because it's very realistic to have that sort of curve thing. But every now and again, it can work a little bit more oddly than you think. But that'll bring us to the end of the programming thing. We actually went over our time here. But I hope it was kind of interesting. If you got questions, go for it. What kind of game would you recommend that you try to recreate as a new programmer? Well, first of all, you have it right in that you should try to recreate a game first as a new programmer because it eliminates all the problems of game design, which is very tricky. Like when you're a new programmer, you have to just learn sort of the actual game sort of programming and development skills, and having to add game design on top of that can be very tricky. And so the best things to try to recreate are things like the really classic games, Asteroid, Pong, Pac-Man. You will learn a lot just trying to do those. And so I think those are the ones you go. Like, go for anything that was on the Atari. That's how you learn. Maybe Super Mario Brothers is your first platform. And literally, like, recreate level 1-1 of Super Mario Brothers as your way of learning. Because, again, all the design questions will have already been solved for you. You just focus on learning the implementations. As the ball moves, the shading changes. Right. I think some of the other things are using the reflection probes in a way that, yeah, that are weird. We need the other things to not care about the reflection at all. I mean, there's a shadow distance, but that's not it. Clear flag. Culling mask. Oh, there we go. We can make it. That would be the way we do it. We'd actually create a new layer for the ball, which is a good idea because you're going to want that for the physics engine anyway. So a new layer for the ball that only the ball is on. And actually, I think culling mask is going to do the opposite thing of what I think. That's the capture. So that's not what we want. That's a good question. We sort of want to tell everything else not to use that, but it shouldn't be at a 0. Yeah, why is that happening? Something's going a little funny there with this reflection probe, and I don't know what that is. It should definitely not be doing that. I mean, one thing that could help, obviously, I mean, this is not the solution, but if we brought the size of the reflection probe so it's so small that it's always inside of the ball itself, then nothing else will ever fall within it. Although the shading in the background is changing a little bit over time. It's actually not the ball. Well, it is the ball. You're right, there's something that's being used as a light source. You know what it might be? It's because the last time we built our lighting model, we were baking in the reflection map. And so all of our static objects might have still been using some weird data. Let me try redoing this. I don't know if this is the solution. No. There's something weird going on there that I don't understand, and I'm just going to ignore it. Pretend it's not happening. Bum, 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 bum. Redo Mario 1-1. Starts Super Mario Maker. Done. All right, we're going to switch over and do some Kerbal Space Program. Although, I've got the Realism Overhaul mod for Kerbal Space Program, which means it's actually got like 30,000 freaking mods basically built into one. And as a result, we've got at least 5 minutes before that boots up. So lots of time for more questions. I hope you guys enjoyed that. I know it was a little bit all over, but it addressed a few, I like the idea of incorporating multiple sort of neat little tricks into one kind of tutorial. We weren't making a pinball game, but we're using it as a context for doing cool things. So I don't know. Reflection probe is rotated together with the ball. Yeah, but it still doesn't explain why everything else is being modified. I don't know. Could be, but nothing else should be touching the reflection probe anymore. Everything else has its reflection set to 0. 0 metalness, so I don't know. Can you try to recreate a U4? I mean, just recreating the map of a U4 would be a really interesting tutorial. Hey, Seabreeze. And who was that right before there? I'm sure there was another bloop that I missed. Oh, Zeratak, thank you very much. Very smooth and shiny, perhaps light sources reflecting off this. That particular type of mechanic is not... We'd have to enable that explicitly. And I think it would look different. No, I don't think... That sort of global illumination, bouncing light, is not something that is just on by default, or shouldn't be. I don't think that's what's going on. The reflection shouldn't be emitting light. That's what people keep going for, but no. I don't... I mean, it might be, and I could check that, but it would feel like, how are we getting that for free? Because that's actually something that's really not simple. Bruin Bob, I release all my code under the MIT license, which basically means you can do whatever you want with it. If you go to quill18.com, there you'll be a link to the Unity tutorials page, which is where you can download all the code for basically everything that I've done. So there you have it. I've never seen a reflection probe used like that. I've done it in my other pinball game. I have it set up like that, and everything works great. I'm not sure where that sort of it's just a weird lighting artifact that's going on. Everything else about it is working perfectly great. The rotation of it shouldn't matter because it's getting mapped perfectly fine. I think the rotation of the reflection probe gets ignored completely, so I think it's irrelevant. We could have it just follow the object, but I'm not sure that's the case. Because I think we were seeing some of that weird behavior otherwise anyway. I could do some other tests and see, but... I ordered in pre-baked fixed light cube map spread across the map. Oh yeah, that's a good point. I mean, so a lot of times you would use, whether it's pre-baked or real-time or whatever, a lot of times your reflection probes don't move. Oftentimes they're in a fixed area, and you would have them sort of like just split up in a section. So as someone, say, moves through the world, they're entering and leaving various reflection probe cubes, and getting sort of new reflection maps getting put on there. It's not necessarily quite as accurate, but it's accurate-ish. And a lot of times you wouldn't even use the real-time ones. You would just use the baked ones, with the idea that like the things that are moving around don't really have real-time reflections, or you sort of fake it with maybe a little bit of an environment map or something like that. Toodle, hey, thank you very much for the sub. And so then it would be just like maybe each room would have one or something like that. If you had a particular showpiece, like if you had a really shiny metal vase in a room, then you might want to have a reflection probe literally right around that one, and you know, maybe even have that one high quality. But as long as it's baked, it's fine. Although if it's baked, then as someone moves up to it, you won't see their own reflection, right? You'll only see the reflection of the room. So you might want to have a real-time one. You can combine them. There's rules for blending reflection probes in Unity that you can check out, and that includes the idea of blending like a super high-res pre-baked reflection map, and then a lower-res real-time one that gets blended together, so you sort of still see yourself. There's a few different ways of doing it. Pinball, where the ball is 90% of your game, is like the only moving probe case I can think of. Yeah, there could be that. You could also imagine a situation where you have maybe an item in your hand that was really reflective, and wouldn't it be cool if that worked with a moving reflection map? It is pretty unusual. It is pretty unusual that your actual reflection probe moves, but it works. The only gotcha is when the reflection probe moves, you absolutely have to do the no time slicing version. Otherwise, the image of the reflection will always be a couple frames behind and will look wrong. Whereas otherwise, the real-time reflection probe is okay. Because 99% of the time, even when things are moving around in the room, the fact that whatever is reflecting the things that are moving around might be a frame or two behind, it's not usually a problem. Visually, it's not usually something that comes up. Although every now and again. Thank you everyone who pledged on Patreon to support these videos back in May, and are therefore keeping this series going from June through to early July. And a special thank to these Mike Check level supporters. We got Speedy Savant, Valiant Cake Fiend, Aaron Toibson, Marius Field Vold, Jan Torrevel, Julien Auger Lafont, Steven Stager, Michael McClintock, Kale the Quick, Drazion, Adjective, Jason Yanity, Wes Oldenboving, Craig Mortel, Neil Bullickley, Milner, and absolutely everyone who watched, shared, favorited, and subscribed these videos. Thank you very much for keeping this series going, and I'll see you next time.